In this lesson, you will learn about optimization problems. Number 1, find the maximum volume of a box that can be made by cutting out squares from the corners of an 8-inch by 15-inch rectangular sheet of cardboard and folding up the sides. So for this problem, we are asked to maximize the volume, and we are starting out with a rectangular sheet of cardboard that has dimensions of 8 by 15 inches. And to form a rectangular box, we are cutting out squares from all 4 corners so that the cardboard looks like this. And each of these squares, we don't know the dimensions, so we are just going to call them X. So instead of having a length of 15, when you cut out these squares, you will have a length of 15 minus 2x, because you cut out a length of x on each side. Instead of having a width of 8, you now have a width of 8 minus 2x. For the same reason, you cut out a length of x on each side. When you fold up the sides of the boxes, this length here becomes the height, and the measure of the height is equal to x. So the length is equal to 15 minus 2x. The width is equal to 8 minus 2x. And the height is equal to x. Since we are asked to maximize the volume, we want to find a formula for the volume of a rectangular box, which is length times width times height. And in terms of x, the length is 15 minus 2x, 8 minus 2x for the width, and x for the height. Anytime you're asked to find the maximum or minimum, you want to take the derivative and set it equal to 0. So to find the volume, I'm first going to FOIL 15 minus 2x Since we're asked to find the maximum volume, we want to first find the volume of a rectangular box, which is length times width times height, and then substitute the length, which is 15 minus 2x, the width, which is 8 minus 2x, and the height, which is x. Find the volume. I will first FOIL 15 minus 2x times 8 minus 2x. And then multiply by x so that I have 120x, and Negative 30x minus 16x is negative 46x, but when I multiply by x, I have negative 46x squared plus 4x to the third. And since we're asked to maximize, we want to take the first derivative and set it equal to 0. So the first derivative is 120 minus 92x plus 12x squared. So if I write this in standard form, 12x squared minus 92x plus 120 equals 0. And divide everything by 4. And then factor. So the two numbers that I will use for 30 are 6 and 5. If I place the 6 here and the 5 here, the outer product gives me 18x, the inner product gives me 5x. 18x and 5x is 23x. Because the second sign is positive, it means both of the signs are the same, and they both get the sign of the first number, so 3x minus 5 and x minus 6. So once the factored form is complete, I set each factor equal to 0. And I get x is equal to 5 over 3, and then x is equal to 6. So if I go back to the length, width, and height, if the length is 6, so if I go back to the length, width, and height, if x is equal to 6, then the length, 15 minus 12, would be 3, but the width, 8 minus 12, would be negative 4. So since we're working with volume and dimensions cannot be negative, x equals 6 is not a possible value, so x is equal to 5/3. But how do I know if this 5/3 is a minimum or a maximum value? The way we know is to take the second derivative. So if I find v double prime negative 92 plus 24x, and if I substitute 5/3 in for x, three reduces with the 24 to 8, and I have negative 92 plus 40. So v double prime of 5/3 is equal to negative 52, and when the second derivative is negative at a critical point, it means it is concave down, and therefore that critical point is a relative maximum. So x equals 5/3 is the value that will give us the maximum volume. So to find the dimensions of this rectangular box, if we take 5/3 and substitute it in for x in the length and x in the width, the length is 15 minus 2 times 5/3, which is 15 minus 10/3, and if I multiply by 3, I have 45 over 3 minus 10 over 3, which is equal to 35 over 3. The width is equal to 8 minus 2x, which is 8 minus 2 times 5/3, which is 8 minus 10/3. So all I'm doing is just finding the values of the length, width, and height so that I can find the maximum volume. And we know that the height is just x, so it's 5/3. So to find the maximum volume, we take length times width times height, so we have 35/3 times the width, which is 14/3, times the height, which is 5/3, and if you multiply these numbers out, you have 2,450 over 27. And if I go back to the beginning of the problem, the box had dimensions measured in inches. So the maximum volume is 2,450 over 27 cubic inches, or inches cubed. For number 2, rectangle ABCD with sides parallel to the coordinate axes is inscribed in the region enclosed by the graph of y equals negative 4x squared plus 4, and the x-axis as shown in the figure below. We want to find the x and y coordinates of C so that the area of rectangle ABCD is a maximum. So we want the area of the rectangle to be a maximum. The area of a rectangle is length times width. So since we want to maximize the area, we'll be taking the derivative of the area. The only thing we know about this rectangle is that it is enclosed in the parabola y equals negative 4x squared plus 4. So if I think of this point here as the point x, 0, and point A as negative x, 0, then I know that the width of this rectangle is 2x, and the height of this rectangle is y, because the coordinates of C are x, y. So the area is equal to 2x times y. Whenever you solve a maximization problem or any optimization problem, you want to differentiate one variable. So we have 2x times y. So I'm going to substitute the y with the negative 4x squared plus 4 that's in the problem. So that area is equal to negative 8x cubed plus 8x. And so I take the derivative of the area and set it equal to 0. And solve for x. And when I take the square root of x squared, I get x is equal to plus or minus the square root of 1/3, which is 1 over the square root of 3, But since I'm asked to find the coordinates of C, and C is to the right of the origin, the x-coordinate must be positive. So I will use the value for x, positive 1 over the square root of 3. So to be sure that this value of x is a maximum, I want to take the second derivative, which is negative 48x, and substitute the value of 1 over the square root of 3 in for x, and I get negative 48 over the square root of 3, which is negative, so it's concave down, which means that the critical point is a maximum. So to find the y-coordinate that corresponds with 1 over the square root of 3, I take the equation y equals negative 4x squared plus 4, and I substitute x equals 1 over the square root of 3 in for x. So I have negative 4 times 1 over the square root of 3 squared is 1 over 3. So that I get y is equal to 8/3. So the value for C has the x-coordinate of 1 over the square root of 3, comma, 8 over 3, or you could rationalize 1 over square root of 3 by multiplying it by the square root of 3 over the square root of 3, which is the square root of 3 over 3, and this point can be written as the square root of 3 over 3, comma, 8 over 3. For number 3, a tank with a rectangular base and rectangular sides is to be open at the top. So if I just draw a rectangular tank, which is basically just a rectangular box, that's open at the top, I will show that like this. The second sentence says it is to be constructed so that its width is 4 meters and its volume is 36 cubic meters. So the width is 4 and the volume is 36 cubic meters. If building the tank costs $10 per square meter for the base and $5 per square meter for the sides, what is the cost of the least expensive tank? So when they give us $10 per square meter, square is an indication that we're finding area. And then another $5 per square meter, another indication that we are finding area. So when they ask for the cost of the least expensive tank, we will be finding the surface area of this tank, take the derivative, and set it equal to 0. So the formula for surface area is to take 2 times the length times the width plus 2 times the width times the height plus 2 times the length times the height. plus 2 times the length times the height. But since this box does not have a top, then you only want one length and width. So the surface area formula is length times width plus 2 times width times height plus 2 times length times height. We know the width is 4, so we'll be substituting in 4 for the width, but the length and height are variables that we do not know the values of. So that's where this volume comes in. The volume of a tank is equal to length times width times height. So if I substitute 36 in for V, 4 in for W, and solve for length times height, I have 9 is equal to the length times the height. So you can solve for either the length or the height. If I solve for the height by dividing both sides by L, I get the height to equal 9 over L. And the reason why I want to do that is so that I will have only one variable in the surface area, so that when I take the derivative, I don't have to use implicit differentiation, which would not apply here. So the surface area is equal to the length times the width, which is 4, plus 2 times the width, again substitute 4. The height I just found to be 9 over the length, plus 2 times the length times the height, which is 9 over the length. And before I take the surface area, its derivative, I will write this as 4L plus 72 over L, or 72L to the negative 1, and then these L's cancel, plus 18. So now when I find the first derivative of the surface area, I only have one variable that I have to differentiate. So the derivative of the surface area is 4 minus 72L to the negative 2 which can be written as 4 minus 72 over L squared and if I find a least common denominator of L squared, I have 4L squared minus 72 over L squared. I want to take this derivative and set it equal to 0 so that I could find the minimum value, since I'm finding the cost of the least expensive tank. So I take 4L squared minus 72. I just need to take the numerator of the first derivative and set it equal to 0. So that 4L squared equals 72. So that L squared is equal to 18. And when I square root both sides, the length is equal to the square root of 18, which can be written as 3 times the square root of 2. I don't need to include the plus or minus 3 square root of 2, because again we're working with volume and dimensions of a rectangular box, and the dimensions of a box cannot be negative. So the length is equal to 3 times the square root of 2. So to make sure that this will give us a minimum value, I want to take the second derivative So if I take the second derivative using this format here, I won't have to use the quotient rule. So the derivative of 4 is just 0, and then negative 2 times negative 72 is positive 144 L to the negative 3, which is 144 over L cubed. So that when I test the critical point of 3 square root of 2, I'm not really concerned with the value of the second derivative, but rather what the sign is. I'm not concerned with the value of the second derivative at 3 root 2, but rather what the sign is. So when I take 3 square root of 2 and substitute it into the second derivative, I get a value that is positive, which means that it's concave up at the critical point, and so therefore it is a relative minimum. So 3 root 2 will give us the minimum dimension of this box, and we want to find the cost of the least expensive tank. So if the length is 3 root 2, we know that the width is 4, the height is 9 over L, so it's 9 over 3 root 2, which simplifies to 3 over root 2. And if I rationalize this, it is 3 root 2 over 2. And we're minimizing the surface area. And the length is 3 root 2. The width is 4. And if we go back to the problem, it says that building the tank costs $10 per square meter for the base, the length and width are the dimensions for the base, and $5 per square meter for the sides. The width and height and length times height are the dimensions for the sides. So therefore, when I'm finding the minimum cost, length and width get multiplied by 10 plus 2 times length times height. So 2 times the length is 3 root 2. The height is 3 root 2 over 2. And I multiply it by 5 for the cost to build the sides, and then I add it to 2 times the width times the height, and once again I multiply this by 5, and then I simplify. 3 root 2 times 4 times 10 is 120 root 2. 3 root 2 times 3 root 2 times 5 is 9 root 4, which is 9 times 2, which is 18 times 5 is 90. Plus 60 root 2. And if I add 120 root 2 plus 90 plus 60 root 2, I get 344.56. So the minimum cost is $344.56. For number 4, this problem has 3 parts. The sum of two non-negative numbers is 20. Find the numbers if, for part A, their product is to be as large as possible. So I will say that the first number is x, the second number is y, and if the sum of these two numbers is 20, I can write x plus y is equal to 20. So I will need this for all 3 parts. And for part A, their product is to be as large as possible. So that means we want the product of x times y to be a maximum. So therefore, I'll be taking the derivative of p. But before I do that, I have to use this equation that I found in the introduction so that I only have one variable. So if I take x plus y is equal to 20 and solve for either x or y, it doesn't matter which variable, so that p is equal to x times 20 minus x, and before I take the derivative I want to distribute, so that p prime is equal to 20 minus 2x, and if I take 20 minus 2x and set it equal to 0, minus 2x equals negative 20, and divide by negative 2, x is equal to 10. So to make sure that this is a maximum, because we want the product to be as large as possible, I want to take the second derivative, and the second derivative is just negative 2, which means that it's concave down, so therefore 10 is a maximum. So to find the y value that corresponds, I take 10 and substitute it in for x so that I get y equals 10. So the numbers that give us the largest product possible is x equals So the numbers that give us the largest product possible is x equals 10 and y equals 10. For part B, the sum of their squares is to be as large as possible. For part B, the sum of their squares is to be as small as possible. So from the introduction of this problem, we will be using the x plus y equals 20 and solving for y again, so that y is equal to 20 minus x. So we will need this at some point in the problem. So this one says that the sum of their squares is to be as small as possible. So that means the sum of the two numbers, x squared plus y squared, is to be a minimum, and before we find s prime, we want to take 20 minus x and substitute it in for y so that I only have one variable. So when I take s prime, I can add either FOIL 20 minus x times 20 minus x, or I can use the chain rule when I take the derivative, so that s prime is 2x minus 2 times 20 minus x, so that s prime is equal to 4x minus 40. So I take 4x minus 40 and set it equal to 0. So that x equals 10. And to make sure that this is a minimum, I find the second derivative, which is 4. Since it's positive, it means that it's concave up, So therefore the critical number of 10 is a relative minimum. So x is equal to 10, so I find the y value to be the same as part A, so x is equal to 10 and y is equal to 10. For part C, one number plus the square root of the other is to be as large as possible. So we will need that x plus y equals 20. For part C, one number plus the square root of the other is to be as large as possible. So we will need x plus y equals 20. And I'm going to go ahead and write this as y equals 20 minus x. And if I translate this sentence, one number plus the square root of the other. So since we're adding, I will write this as the sum equals, or just s equals, one number plus the square root of the other. So I can write this as x plus the square root of y, or y plus the square root of x. It doesn't matter. So if I rewrite this as x plus the square root of 20 minus x, the square root of 20 minus x is the same as 20 minus x to the 1/2. I can now take the first derivative using the chain rule, so that s prime is equal to 1 minus 1 over 2 times the square root of 20 minus x. So I want to write this as one fraction so that I can set the derivative equal to 0. So that I have 2 times the square root of 20 minus x minus 1 over 2 times the square root of 20 minus x. And if I take the first derivative and set it equal to 0, I take 2 times the square root of 20 minus x minus 1 equals 0. And solve for x. And I square both sides, so that 20 minus x is equal to 1/4. And if I subtract 20, negative x is equal to 1/4 minus 20 is negative 19 3/4. Divide both sides by negative 1, and x is equal to positive 19 3/4. So to make sure that x is equal to 19 3/4 will give us a maximum because we want this to be as large as possible. I take the second derivative, using this form, and I substitute s double prime with 19 3/4 and if I look at the numbers underneath the radical, 20 minus 19 3/4 is a positive number, cubed is a positive number, and then the square root is a positive number. So I'm not so concerned with the value, but the sign. So since this comes out positive, we know that this is concave up, so if I rewrite the first derivative in this form, I have 1 minus 1/2 times 20 minus x to the negative 1/2, and I take s double prime, which is positive 1/4 times 20 minus x to the negative 3/2. I subtract 1 from negative 1/2, and then using the chain rule I take the derivative of what's inside, which is negative 1. I can write the second derivative as negative 1 over 4 times 20 minus x to the power of 3/2. So that when I take 19 3/4 so that when I take 19 3/4 and substitute it in for x in the second derivative, I'm not concerned with the value of the second derivative of 19 3/4, but rather the sign. So 20 minus 19 3/4 is a positive number. When I raise that to the 3/2, it's also positive. So my entire denominator is positive, but the numerator is negative. So therefore, the answer will be negative. And if it's negative, it's concave down, which means that the critical point is a maximum. So I know that the value of x, 19 3/4, is the value that gives me a maximum sum. So to find y, I know that y is equal to 20 minus x. So 20 minus 19 3/4 is equal to 1/4. So y equals 1/4 and x equals 19 3/4. For number 5, a farmer wishes to enclose a rectangular field by a fence and then divide it down the middle by another fence parallel to the sides. So let's draw a rectangular field divided down the middle so that we know these two parts and these two parts are all congruent to each other. What are the dimensions of the largest area that can be enclosed with 1,800 feet of fencing? So we are trying to maximize the area. The area of a rectangle is length times width, so we will be taking the first derivative of the area. But this 1,800 feet of fencing means that if you were to have 1,800 feet of fencing, it would have to cover all four sides of this rectangle plus this dimension in the middle. So I'm going to use x's to represent these three sides and y's to represent the four congruent parts, so that this 1,800 is equal to 3x's plus 4y's. So in terms of x and y, the area, the length is 2y and the width is x. So area equals 2 times y So in terms of x and y, the length is equal to 2y and the width is equal to x. But once again, we don't want to take the derivative with a y and an x. We only want to use one variable. So I'm going to solve for y, so that 4y is equal to 1,800 minus 3x so that y is equal to 450 minus 3/4 x So if I write 2x times y, just reverse the two letters, and then 450 minus 3/4 x and distribute, I can simplify this as 900x minus 3 over 2 x squared, so that the first derivative is equal to 900 minus 3x, and if I take 900 minus 3x and set it equal to 0, negative 3x equals negative 900. X is equal to 300. But to make sure that this gives us a maximum, I want to find the second derivative, which is just negative 3. And since it's negative, it's concave down, which means that x equals 300 is a relative maximum. So if x is equal to 300, I take that value and substitute it in for y, so that y is equal to 400 minus 225 So I take 300 and substitute it in for x, so that y is equal to 225. So x is 300 and y is 225. So if I go back to the original question, the question is asking for what are the dimensions of the largest area. So if this is the width is equal to 300, and if this is the length is equal to 2y, which is 2 times 225, which is equal to 450. So the dimensions that give us the largest area are 450 and 300.